Good morning. In this video, we are going to discuss about this voltage divider bias for this BJT circuit. So there are DC analysis and small signal analysis. In this video, we will discuss the DC analysis, and the next video we will discuss the small signal analysis. First, we will start with the DC analysis. For voltage divided by a circuit, you can see there are two resistors R1 and R2. When comparing it fixed by a circuit, it has one resistor RB that is connected to the base. In voltage divided bias, there is two resistors R1 and R2. For DC analysis, we know capacitor, open the capacitor. So when we open the capacitor, this CC we have to remove CC. This capacitor is open. So what happened to this VS and RS? The VS and RS get isolated from the rest part of the circuit. So in the DC circuit, we have only R1, R2, this transistor, RC, RE and VCC. So I will redraw the DC circuit. This is R1 and this is R2 and this is RC, this is VCC and this part is grounded. So this is the collector terminal and this is the base terminal and this is the emitter terminal. Okay. So we have to calculate the Q point. For end of the DC analysis, we have to draw the load line and we have to calculate the Q point. We should know what is VCQ and ICQ. First you have to do the input loop analysis and calculate what is IBQ and ICQ. Do the output loop analysis and calculate what is DCQ. Now, I'm going to draw the Thevenin's equivalent to the left of this point. So, I will redraw the circuit. There is a VCC. The negative of VCC is grounded. The positive of VCC is connected to R1. This is connected to R2. This R2 is grounded. So this is the base point. Just I have drawn the circuit to the left of this dotted line. There is a VCC. From the VCC there is a R1. After that there is a R2 connected to ground. And the potential at this point is VB. So this whole circuit I am going to replace it by its Thevenin equivalent. How to draw the Thevenin equivalent? There is any circuit can be replaced by a single voltage source and a resistance which is the Thevenin's equivalent resistance. So this will be grounded. The entire circuit VCC, R1 and R2 is going to be replaced by, and this is the point B. The VCC, R1 and R2 are going to replace by a VTH and a RTH. So now we have to calculate what is VTH and RTH. What is VTH? The voltage across this point between B and the base terminal is VTH. So by voltage division rule, what is VTH? VTH is the voltage across this R2. So by voltage division rule, which is total voltage multiplied by R2 divided by R1 plus R2. So this is VTH. Now how to calculate RTH? If you want, you can go and study the Thevenin's equivalent, how to calculate RTH in doing Thevenin's model. So while calculating the RTH, we have to nullify all the DC voltage sources. So if you make VCC to 0 A circuit looks like this is ground because I have made VCC to 0 and there is R1 and R2. So here you have to calculate what is RTH. This is R2 and this is R1. What is RTH seen from this point? What is the equivalent resistance will give RTH. If you see from here, R1 and R2 are in parallel. This is R1 and R2, two resistance are in parallel. So RTH equal to R1 parallel R2. So I know what is VTH, I know what is RTH. Now I am going to replace this VCC R1 and R2 by VTH and RTH. I will redraw the circuit. This is RE, the RC, other end of RC is connected to VCC. Previously we have this R1 and R2. Now instead of this R1 and R2, we are going to replace by RTH and VTH. You know what is RTH and VTH. Now this is the circuit. The voltage divided by R is now simplified to this circuit with VTH and RTH. From this circuit, you have to do the input loop equation and output loop equation. So now what is the current flowing through? This is IC, here it is IB, and here it is IB. Now KVL at the input side. I'm going to write a KVL here. You know that this is the emitter point. This is the emitter. The voltage drop between the base and the emitter, we will write it as VBE. Now this forms a closed loop here. I will start from this VTH. So it is minus VTH minus VTH plus IB multiplied by RTH plus VBE plus IE RE equal to 0. So this is the input loop equation. Again I will repeat. So I will start from this VTH. So it is minus VTH. So this is the direction of the current. It is minus VTH plus IBRB plus VBE plus IERE equal to 0. This completes the loop. Now from this, I want to calculate IB. So what is the relation between IB and IE? IE equal to IC plus IB. So from this equation, IC can be written as IC equal to beta IB plus IB, that is equal to 1 plus beta IB. So instead of this IE, I can replace with 1 plus beta IB. So minus VTH plus IB, IB is common, which is RTH plus 1 plus beta RE plus VBE equal to 0. What is IB then? IB equal to VTH minus VBE divided by RTH plus 1 plus beta RE. So once IB is calculated, you can calculate what is IC and IE. What is IC? IC is beta IB. What is IE? IE is IC plus IB. Now we have to proceed with the KVL at the output side. So output side KVL, there is some VCC here. After that there is the ICRC. From this is the collector point. From the collector to the emitter, there is a voltage drop of VCE. So the positive of VCC is connected to resistance and the negative of VCC is grounded. So writing KVL at the output loop, minus VCC plus ICRC plus VCE plus IERE equal to 0. So here if you want, you can write IE in terms of IC. So how to write that? IE equal to IC plus IB. So IC plus, instead of beta you can write IC by beta. That is equal to IC multiplied by 1 plus beta divided by beta. So here I can substitute BCE equal to BCC minus ICRC minus IC multiplied by 1 plus beta divided by beta RE equal to 0. So that is equal to BCC minus RC multiplied by IC multiplied by RC plus 1 plus beta divided by beta RE. So in this equation, if beta is very much larger than 1, what happens? This 1 you can neglect. So beta is very much larger than 1, we can approximate 1 plus beta as beta. So numerator it is beta, this beta and beta will get cancelled, which is equivalent of saying approximately VCC minus IC multiplied by RC plus RE. So what is the meaning of this? In this equation, from this equation, if you assume IC is approximately equal to IE. Why IC is approximately equal to IE? If you see IE equal to IC plus IB. IB it will be in the terms of microamps and IC will be in the terms of milliamps. So you can approximate IC is directly, IB is negligible because it is in microamps. So we can approximate IC is approximately equal to IE. So if you do that, you can, instead of this IE, directly you can substitute IC. So you will get VCC equal to minus of IC multiplied by RC plus RE. So this is VCE. So to draw the load line, this is VCE and this is IC. First you have to calculate what are the endpoints here and here. So you know that to calculate this point in the x-axis we have to make IC equal to 0. So from this, if you make IC as 0, BCE equal to BCC. This point is VCC. To calculate this point, we have to make BC as 0. BC as 0. IC equal to BCC divided by RC plus RE. So this point is BCC divided by RC plus RE. And how to calculate the Q point? We have calculated. So this is IBQ. This Q represents Q point. This is IBQ, ICQ and IEQ, and this is BCEQ. Okay, in the next video we will discuss the small signal analysis for the voltage to the